The question of life in the universe is a complicated one. Our brand of life here on Earth required warm temperatures, liquid water, and the chemicals required for life to function to all come together just so to produce abiogenesis, the advent of life. How exactly this happened is still largely a mystery. We don't know the exact circumstances of how that occurred. But what we do know is that the organic chemical reactions involved tend to happen very quickly, and indeed they seem to have happened at the very earliest moment they could on this world, which was during the late heavy bombardment, which were far from ideal conditions for delicate reactions to occur. This of course leads us to the question of whether life was seeded here through the interchange of meteorites through panspermia from other bodies in the solar system that might at the time have been more amenable to abiogenesis. The natural candidate here is Mars, but there's also Venus, but even moons like Europa or Titan or even the asteroid Ceres, which were very different back in the early days. Make no mistake, it's fully plausible and within the rules of science that life on Earth might not have originated here. Indeed, it can even be speculated that as early life arose on Earth some 3.8 billion years ago, the Sun might still have been close enough to its birth cluster siblings for life to have transferred on an interstellar basis, opening up the way for genetically related life to be actively spreading itself among the entire galaxy as the birth cluster dissipated. These speculative possibilities aside, there's also the glaring question of the age of our solar system. It's about 4.6 billion years old, formed at a time when suitable heavy elements had populated the galaxy as to be ubiquitous. There was no shortage and still is no shortage of materials in the Milky Way to promote planet formation. Indeed, we see the infrared glow of the warm dust and gas of protosolar systems throughout the galaxy, and the youngest known exoplanet is only a few million years old. And indeed, we also see the hallmarks of basic organic chemistry in the clouds that populate the Milky Way. We also see the hallmarks of water readily, one of the most common compounds in the universe. Albeit mostly in ice, but stars are warm and can heat up planets enough for liquid. But even planets themselves, with radioactive decay heating, can do it too. The very most basic conditions and building blocks of life as it arose and evolved on Earth seem to present something easy. Wait long enough and life will happen, and when it does happen it may spread itself to other worlds, either through microbes trapped in rocks or spacefaring civilizations colonizing other worlds. But that is the Fermi paradox. When we look at the galaxy, so far, as our rather crude and imprecise current instruments show us, we see nothing but a great silence. This silence will no doubt get even more deafening should we find independent examples of abiogenesis in the oceans of the solar system's ice shell moons. Find life once in a star system, it might be a fluke. Find it twice, totally unrelated, and at least simple life must be very common indeed among the stars. Indeed, should it have happened twice or even 3 times in a single star system, then that would suggest that the galaxy hosts millions of occurrences of life, and the universe at large, countless occurrences, and the question becomes not one of abiogenesis, but how often life leads to technological civilizations. But if we assume that there are no great filters to the advent of life itself, then we confront the questions of how hard and situational it is for life to yield intelligence and technology. This involves one overarching factor, however, time. It took Earth billions of years for the conditions to present themselves for a civilization to arise that also happens to be biologically suitable to create technology. To some that ponder the Fermi paradox, this suggests that we might be very early in the game, appearing among the earliest moments that intelligence could in the universe. This presents interesting scenarios, because if there are other technological civilizations in the galaxy, they may not be all that more advanced, or less so than we are. By this I mean within a few million years of each other technologically, which can be quite a gap of course, but in the grand scheme of things still Kardashev type 1 or 2 civilizations, those that control planets or star systems but not galaxies, explaining the apparent lack of a galaxy-spanning Type 3 civilization in the Milky Way. This stands in the face of statistical likelihood, however. Carl Sagan once noted that on that basis, it's highly unlikely for any civilization we come across to be at our level. Rather, they would be far ahead or far behind. Rather, more recent work done by David Kipping and others suggests that the most likely scenario is to run across intelligence in the galaxy far and away more technologically advanced than we are. We are not likely to meet our equals, as generally happened in Star Trek, but are technological superiors that are orders of magnitude more advanced than our fledgling civilization that's had meaningful radio scarcely for 100 years. Even control of the electromagnetic spectrum at large is new. Not that long ago, we haphazardly made do with the light of fires and candles. And only now, the electronic LED. Within my own lifetime, I myself remember when thoughts of LED lighting was confined to colored plastic lights like you'd find on a university mainframe, or an electronics experiment toy from Radio Shack. Now LEDs are stoically replacing the incandescent light bulb, as they once did the tallow candle and oil lamp, but without the nostalgic mystique. Someday, those bulbs may be exceedingly rare in functional order. The last functioning incandescent light bulb auctioned off by a major auction house to the last holdout of such things in a few centuries aside, we'll call him Chuck, here we come back across the materials needed for life. Many of them are heavier elements that the universe was not born with, the Big Bang only having created the very lightest elements. The rest came later, born in the cores of stars that went supernova, and other situational cases like kilonovas and nuclear transmutation in scientists' labs, be it alien or human. So here's the natural question. How old can the oldest civilization in the universe actually be? This question does not cover life itself. There was a time known as the Epoch of Habitability, where the residual heat from the Big Bang made everywhere effectively habitable as far as temperature goes. This short-lived period could have allowed for primordial microbial life to form just about anywhere in the universe, should the materials needed for it have been present. Unlikely, but not out of the question. But what's highly unlikely, to put it mildly, was for a civilization to form during that epoch. But when exactly did it become possible? The answer is simply staggering, or at least potentially so. The exoplanet PSR B1620-26b is one of the oldest known exoplanets, and indeed among the first ever discovered. It's an exoplanet about 2.5 times the mass of Jupiter, but in a very strange environment indeed. Sitting in a globular cluster, the planet orbits a pair of stars consisting of a white dwarf and a pulsar, both burned out remnants of a star system. Known as Methuselah or the Genesis planet, it's not only the first planet found in a globular cluster, but also one of the first found to be orbiting a pair of stars, or in this case, former stars. It's unclear how this planet has survived, given its environment, and probably should have been ripped apart or ejected, yet it exists. This might be because the planet could be a capture of sorts, in that it most likely formed around the former star that became the white dwarf, which itself was captured by the neutron star in the dense environment of the cluster. And now the planet has migrated to its current position, orbiting both. This is a complicated situation. So the white dwarf was originally probably a relatively normal main sequence star, but was captured by the neutron star sometime within the last 10 billion years. The neutron star might have lost an original companion star in the process. As the normal star expanded into a red giant phase, thought to be about 500 million years ago, it lost mass to the neutron star, robbing it of material, for which there is evidence in the pulsar's spin period, which is milliseconds as opposed to a second or so. This only happens when a pulsar accretes matter from a companion and gets spun up as it gains mass. This would have subjected the poor planet to an intense period of X-ray radiation as that process unfolded. So this planet has more counts against it on the life possibilities than most other exoplanets in the universe. But now to the big question. How old is this exoplanet? The answer is derived from a known phenomenon. All members of globular clusters tend to be similar ages, in that they all formed more or less at the same time. So the star that the exoplanet originally orbited is likely to be as old as the pulsar, and it's a staggering 12.7 billion years old, in a universe thought to be 13.8 billion years old. You're looking at planets in the universe as early as only 1 billion years after the Big Bang, and 3 times older than Earth. That aside for a moment, it's interesting to see what's going to happen to Methuselah. It can't stay in the conditions that it's currently in forever. Instead, the entire star system is slowly moving towards the center of the globular cluster, sinking as it were. This means that in a billion years or so, it will enter an even denser region, with numerous and ongoing close encounters with other stars. When this happens, the physics are such that the lightest member of the system, the exoplanet, will get ejected and will either wander the cosmos as an interstellar rogue planet or get captured by another system, though less likely so. It may just end up wandering the globular cluster forever. But at an age of 12.7 billion years old, this planet shows that the materials needed for planet formation were available a very long time ago, opening up the possibility of Earth-like planets and life much earlier than it happened here. If you assume that there's no faster path to intelligence and evolution, which there may well be, and you use Earth as the measurement, then it would have been possible for civilizations to arise as early as a comfortable 8 billion years ago, if not before. This might mean that there are indeed civilizations that are many billions of years older than our own out there, of a level of technology we can't even envision. But it does add another dimension to the Fermi paradox. If civilizations could have arisen any time within the last 8 billion or more years, then why don't we see ready evidence of them? The answer must be that either we don't know what we're seeing, or they simply aren't there, leading to the myriad proposed solutions to the Fermi paradox. But one thing is clear, if we never see anyone, then there is some variation, one way or another, of a great filter, making our own existence somewhat spooky and very lucky indeed. Thanks for listening. I'm futurist and science fiction author John Michael Godier, currently addressing those detractors that are very noisy about how astronomers name stars and celestial objects. If it's not some word salad catalog number like KIC 8462852, it's something like Oumuamua. Well, how about this? The first ever exoplanets discovered also orbit a pulsar, 3 of them. And they have been known long enough to have been properly named by astronomers. What did they come up with? Draugr, Poltergeist, and Phobitor. Not kidding. I'll just let myself out, and be sure to check out my books at your favorite online book retailer and subscribe to my channels for regular, in-depth explorations into the interesting, weird, and unknown aspects of this amazing universe in which we live.